Alright, hello everyone, and welcome to my channel. This channel is for educational purposes, and we look at a lot of, or we slowly move through theories of everything, do deep dives on them, and kind of show you how to operate them, what their basic ideas are, and how you can use them in your own life to improve your paradigm shifting or your awakening to 5D consciousness. And today is our 483rd video on the reciprocal system of theory from Dewey B. Larson. And Larson was an American engineer, lived in the 20th century. Around 1959, he proposed his two fundamental postulates about how the universe operated. Just two sentences that articulated his reciprocal system, or other people would call it the universe of motion. Larson was one of the few scientists to try to build his universe upon motion, not matter, or not energy, or not force, but motion. And, there had been some predecessors, such as Thomas Hobbes and René Descartes. But Larson, I think, distinguished himself as far as that goes, and turned it into a generalized theory, first by defining motion as the relationship between space and time, and also by kind of defining motion, the motion that he's talking about, as scalar motion. This is a motion that is a little bit different from the vectorial motion that we're accustomed to. A scalar motion is a motion that has a magnitude, but it has no specific direction. So you can envision this using a balloon that you put dots on. If you blow up the balloon, all the dots will be moving away from each other, but in no specific direction. And it's really, not so much the motion of the spots on the balloon. It's the motion of the literal fabric that the balloon is on. The balloon surface is what is expanding. And so that is kind of the analogy that you're using for this idea of motion. The dots on the balloon are just along for the ride, and the balloon itself is expanding. And this was used by Larson as, the basic idea of the Hubble and his associates that determined almost 100 years ago that all of the distant galaxies are moving away from each other. So this is a comparable motion to that, according to Larson, even though the scientists at the time used it to come up with the Big Bang model. But the Big Bang model posits that there is a center point from which all of those distant galaxies are expanding, which is where we are. So that's a dubious, stance to take, that we're not participating in this expansion of the distant galaxies, because we're at the center. Larson is saying that our galaxy is also participating in this expansion of space. It's not an expansion of the galaxies in space. It's a literal expansion of space itself. And that time also undertakes this same type of expansion. Anyway, If you want a more detailed description of the reciprocal system, just watch any of my first 474 videos on this topic, where I go into 15, 20, or even more minute description of the reciprocal system and how it operates. But for these purposes, I'm going to just kind of assume that you know something, or else that you're adventurous enough to go into territory that you don't kind of have the background. I'll just tell you that the two fundamental postulates that Larson pronounced, then from there he deduced a theoretical universe, how the universe would look if his postulates were correct, and then he compared his theoretical universe with the measured empirical universe of the legacy scientists to see, how they compared. And we're looking at one of his books that does that, called Basic Properties of Matter, primarily on chemistry, on the basic properties of matter, such as the melting point and boiling point, and specific heat, and the compressibility. And we're looking at about to start chapter 11 here, called Thermoelectric Properties. Now, Larson's first postulate is where his original findings from his inductive study that preceded the postulates proceeds. And his first postulate is that the universe is composed entirely of one component, motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. Okay, so Larson is saying that the universe is made out of motion, but that motion is a scalar motion. That is the source of everything else, and that motion is always existing, omnipresent and eternal, and that motion is the relationship between space and time. Space and time have no other existence other than to exist together in motion. Motion is a fraction, with space or time as the numerator and time or space as the denominator. And all of our scientific phenomena are forms of motion. Matter is a form of motion. Energy is a form of motion. Electric charge is a form of motion. Pressure is a form of motion. They all have their space-time signatures, keeping in mind that time, space, and motion come in 3 dimensions. And time, space, and motion also come only in discrete units, as do the units, or the kinds of motion. Speed, energy, matter, they all come in units. And those units are made out of units of space and time. Okay, let's start to read here on thermoelectric properties. We just kind of got done with this chapter on electrical resistance. And I have to admit that I was a little bit stumped at the end there. I still can't really figure out why how he gets this pressure resistance equation from it being the reciprocal of the pressure volume equation. But maybe I'll figure it out. I tried to rack my brain on it a little bit last night to no avail. I feel like I'm getting close. I'm knocking on the door. But perhaps Larson will say something here in this chapter that will ring a bell and help me understand that. Or perhaps you will and put it in the comments section. But let's start this chapter on thermoelectric properties. As brought out in chapter 9, which was on electric current. As brought out in chapter 9, the equivalent space in which the thermal motion of the atoms of matter takes place contains a concentration of electrons, the magnitude of which is determined in the first instance by factors that are independent of the thermal motion. In the thermal process, the atoms move through the electron space as well as through the equivalent of extension space. Where the equivalent of extension, where the net time displacement of the atoms of matter provides a time continuum in which the electrons, or the units of space, remembering that Larson posited that the electron is a rotating unit of space, and that electrons can be both charged and uncharged, and the uncharged electron is the electric current. And the electric current, being made out of space, it moves through time, because the relationship between space and time is motion. And an atom is primarily made out of time. But some kinds of atoms have a large space component. And those that have the large space component would be known as insulators, while the ones that are made primarily out of time would be the conductors. Okay, so where the net time displacement of the atoms of matter provides a time continuum in which the electrons, the units of space, can move, a portion of the atomic motion is communicated to the electrons. The thermal motion in the time region environment therefore eventually arrives at an equilibrium between motion of matter through space and motion of space through matter. And I guess that motion of matter through space is the thermal motion. Or perhaps not. Let's see. It should be noted particularly that the motion of the electrons through matter is a part of the thermal motion, not something separate. Okay, so the motion of electrons through the matter is also a part of the thermal motion. And apparently that's true regardless of whether that matter is made out of time or made out of a combination of time and space. I thought that if you had superconductivity, the atoms, the electrons would move through the matter without generating any thermal motion. But perhaps I'm missing something. So, okay, a mass M attains a certain temperature T when the effective energy of the thermal motion reaches the corresponding level. It is immaterial from this standpoint whether the energy is that of motion of mass through equivalent space or motion of space through matter. Now, the equivalent space is just the two-dimensional region that we see of an atom moving in the time region. And the time region is because it's occurring within 1 unit of space. And through the discrete unit postulate, if you don't have a full unit of space, you don't have space at all. And all the motion is therefore occurring in time. But since we are anchored to a spatial reference system, we do not see time. We only see space, and so we see the equivalent of the time region motion in space, but the equivalent space is a second power region, and so has to be you see two dimensions where there's only one. It's a projection. But that doesn't help me to understand. It is immaterial from this standpoint whether the energy is that of motion of mass through equivalent space or motion of space, that being electrons, motion of uncharged electrons through matter, or a combination of the two. In previous discussions of the hypothesis that metallic conduction of heat is due to the movement of electrons, the objection has been raised that there is no indication of any increment in the specific heat due to the thermal energy of the electrons. The development of the reciprocal system of theory has not only provided a firm theoretical basis for what was previously no more than a hypothesis, the electronic nature of the conduction process, but has also supplied the answer to this objection. The electron movement has no effect on the specific heat because it is not an addition to the thermal motion of the atoms. It is an integral part of the combination motion that determines the magnitude of that specific heat. Because the factors determining the electron capture from and loss to the environment are independent of the nature of the matter and the amount of thermal motion, the equilibrium concentration is the same in any isolated conductor, irrespective of the material of which the conductor is composed. The temperature or the pressure. Let me read that sentence again. Unfortunately, the sentence is 6 lines long, okay? Because the factors determining the electron capture from and loss to the environment are independent of the nature of matter and the amount of thermal motion, the equilibrium concentration is the same in any isolated conductor, irrespective of the material of which the conductor is composed, the temperature or the pressure. Okay, so he's taken out the atomic composition, what the matter is. He's taken out the temperature and he's taken out the pressure. None of these are factors. The only factors the equilibrium concentration is the same in any isolated conductor. Okay, so as long as the conductor is isolated, the equilibrium concentration is the same. Okay, well, I could have used a little bit more of an explanation on that, but be that as it may, let's continue. All of these factors do, however, enter into the determination of the thermal energy per electron. Like the gas pressure in a closed container, which depends on the number of molecules and the average energy per molecule. The electric voltage within an isolated conductor is determined by the number of electrons and the average energy per electron. In such an isolated conductor, the electron concentration is uniform. The electric voltage is therefore proportional to the thermal energy per electron. He seems to be making some leaps here that I'm not following. The coming rapid fire. I'm getting discouraged, but you should not, because, you know, just let it wash over you. Try to pick up the breadcrumbs that you can pick up, understand what you can understand, and, you know, suspend disbelief, but also suspend belief. Just kind of let these things marinate, and hopefully eventually some answers will pop out. But that's pretty much how you have to study Larson, or pretty much how you have to study any type of esoteric subject. You're going to be hit with stuff you don't understand. And you just have to kind of continue to move on and understand what you can understand and build from that. So, you know, just try to keep in mind what you do understand, from, you know, not from your former paradigm, but from, you know, what you've gleaned so far from the text and, you know, from the postulates and so on. The energy level at which the electrons are in thermal equilibrium with the atoms of a conductor depends on the material of which the conductor is composed. If two conductors of dissimilar composition, copper and zinc, let us say, are brought into contact, the difference in the electron energy level will manifest itself as a voltage differential. A flow of electrons will take place from the conductor with the higher or the more negative voltage, the zinc, to the copper until enough electrons have been transferred to bring the two conductors to the same voltage. What then exists is an equilibrium between a smaller number of relatively high energy electrons in the zinc and a greater number of relatively low energy electrons in the copper. In this example, it is assumed that the voltages in the conductors are allowed to reach an equilibrium. Some more interesting and significant effects are produced where equilibrium is not established. For instance, a continuing current may be passed through the conductors. If the electron flow is from the zinc to the copper, the electrons have the zinc with relatively high voltage that prevails in that conductor. In this case, the lower voltage of the electrons in the copper conductor cannot be counterbalanced by an increase in the electron concentration, as all of the electrons that enter the copper under steady flow conditions pass on through. The incoming electrons, therefore, lose a portion of their energy content in the process of conforming to that new environment. The difference is given up as heat, and the temperature in the vicinity of the zinc-copper junction increases. If the section of the conductor under consideration is part of a circuit in which the electrons return to the zinc, this process is reversed at the copper-zinc junction. Here, the energy level of the incoming electrons rises to conform with the higher voltage of the zinc, and heat is absorbed from the environment to provide the electron energy increment. This phenomenon is known as the Peltier effect. In this Peltier effect, a flow of current causes a difference between the temperatures at the two junctions. The Seebeck effect is the inverse process. Here, a difference in temperature between the two junctions causes a current to flow through the circuit. At the heated junction, The increase in thermal energy raises the voltage of the high energy conductor, the zinc, more than that of the low energy conductor, the copper. Because the size of the increment is proportional to the total energy. A current therefore flows from the zinc into the copper and on to the low temperature junction. The result at this junction is the same as in the Peltier effect. The net result is therefore a transfer of heat from the hot junction to the cold junction. Throughout the discussion in this volume, the term electric current refers to the movement of uncharged electrons through conductors, and the term higher voltage refers to a greater force, force being T over S squared, due to a greater concentration of electrons, or its equivalent, in a greater energy per electron. This electron flow is opposite to the conventional, arbitrarily assigned direction of current flow, utilized in most of the literature on current electricity. Ordinarily, the findings of this work have been expressed in the customary terms of reference, even though in some cases the findings suggest that an improvement in terminology would be in order. In the present instance, however, it does not appear that any useful purpose would be served by incorporating an unfortunate mistake into an explanation whose primary purpose is to clarify relationships that have been confused by mistakes of other kinds. A third thermoelectric phenomena is the Thomson effect, which is produced when a current is passed through a conductor in which a temperature gradient exists. The result is a transfer of heat either with or against the temperature gradient. Here, the electron energy in the warm section of the conductor is either greater or less than that in the cool section, depending on the thermoelectric characteristics of the conductor material. Let us consider the case in which the energy is greater in the warm section. The electrons that are in thermal equilibrium with the thermally moving matter in the section have a relatively high energy content. These energetic electrons are carried by the current flow to the cool section of the conductor. Here, they must lose energy in order to arrive at a thermal equilibrium with the relatively cold matter of the conductor, and they give up heat to the environment. If the current is reversed, the low energy electrons from the cool section travel to the warm section, where they absorb energy from the environment to attain thermal equilibrium. Both of these processes operate in reverse if the material of the conductor is one of the class of substances in which the effective voltage decreases with an increase in temperature. There are also some substances in which the response of the voltage to a temperature increment changes direction at some specific temperature level. A similar reversal of the Thomson effect occurs whenever a change of this kind takes place. The quantitative measure of the capability to produce the thermoelectric effects is the thermoelectric power of the various conductor materials. This is the electric voltage expressed either relative to some reference substance, usually lead, or as an absolute value measured against a superconducting material. Neither the theoretical study nor the experimental measurements are far enough advanced to make a quantitative comparison of theory with the experimental results feasible at this time. But some of the general considerations that are involved in the quantitative determination can be deduced from theoretical premises. The basic difference between the thermal motion of the electrons and that of the atoms of matter is in the location of the initial level, or 0 point. The 0 for the thermal motion of the atoms is the equilibrium condition, in which the atom is stationary in a three-dimensional coordinate system of reference, because the motion imparted to it by the progression of the natural reference system is counterbalanced by the oppositely directed gravitational motion. On the other hand, the 0 for the thermal motion of the electrons, the magnitude of the motion of the electrons in the absence of thermal motion, is the natural 0, in which in the context of the stationary reference system is unit speed, the speed of light. The measure of the energy of the electron motion in matter is the deviation of the speed upward or downward from this unit level. The fact that the 0 energy levels of the positive and negative electron motion are coincident explains why each thermoelectric effect is a single phenomenon in which the 0 level is merely a point in a continuous succession of magnitudes rather than a discontinuous phenomenon such as the resistance to current flow. The difference between a small positive electron speed and a small negative electron speed is itself relatively small, and within the limits of what can be accomplished by a change in the conditions to which the conductor is subject. Such a change in conditions may therefore reverse the motion. But a substance that is a conductor in one temperature or pressure range does not become an insulator in another range, because the positive 0 is the equivalent of the negative infinity rather than the negative 0. And in application to the atomic motion, there is, as a consequence, an immense gap between a small positive thermal speed and a small negative speed. Okay, we're going to leave it there for today and take over tomorrow with the next section on thermoelectric properties. Just keep in mind that this is a general study, and so what we learn about thermoelectric properties we can apply to other aspects, and that's the important part. Okay, thanks for tuning in.